Okay, so now it is my great pleasure to introduce our keynote speaker for today, Glenn Troberg. Glenn received his PhD from Rutgers University in 1990 under the direction of Ron Graham, who's now with UCSD. He then came to ASU immediately after that. We have not let him go, and we will not let him go despite there being several suitors. And so Glenn, you're staying right here, right? So
that's not you here.
Yeah. Just be clear, that's a university suitors, not. Glenn is an expert in discrete mathematics and in particularly universal cycles and graph beveling and extremal set theory, in which I believe is going to be a course this semester. And he's going to speak to us on Mathemagics. Glenn? Just one last thing is that we will have a random drawing, and the sort of counting out the ballots will be supervised by the Arthur Anderson accounting firm. Sorry, bad joke. And that'll be held at the end of Glenn's talk, and the winners, approximately 50 of whom, will win a book of their choice. Okay, so if you'd like to be part of that, please do stay here at the end of the class. Glenn?
Well, thanks. First and foremost, welcome to Matthias and David for inviting me to do this. I haven't been able to get here early in the morning. We had a lot of family stuff to do, which was equally fun. But I hope that everybody's had a fun time here. I hope you'll have a fun time from now on out, or else I'm in trouble. So what I want to do to start is talk about some things that are mathematics that a lot of people don't normally think or know are mathematics. I always think of my sister when I talk about this, because she struggles with arithmetic. She would call me up, as an adult, and she'd say, how do you do tax? And I said, what do you mean? You trying to leave a tip or trying to figure out? And she'd say, well, I just want to know what numbers to punch on the calculator. Okay, so we go through it. She always struggled as a kid, and my parents had records that they tried to. She loved singing all the songs in the commercials, and to this day, she could tell you what was the jingle for this and that. She could do all of Schoolhouse Rock. And so my parents thought it would be a great idea to have a record that just sang the multiplication tables, and even that didn't work. So she wasn't going to be Buffalo. One thing that she was good at, though, was spatial relationships. She was fantastic at doing these types of puzzles. Anybody ever seen these?
Yeah. Yep.
And I don't know if you can see this well, but there's a ring here that is just, the rest of this iron stuff is it's too hard to get off. It's too fat, too wide. And so the object is to try to get it off. And so when you do, you realize it's just impossible. You just can't quite get anything around. And the thing about it is that she was really good at this stuff, much better than I was, and she could hold this thing up and somehow get it off. So they're kind of fun to do, and it just seems like recreational fun. But it turns out when you get old enough, you take a course in graduate school called topology, or some undergraduates take this. And topology is all about these kinds of spatial relationships, about how do you work these things, and how do you put them on, take them off, and what have you. And well, apparently you can't put them back on. So, although you can try, but there you go. All right? So, and there are others, and some of my students who are here know that if you don't do well on one of my exams, I lock you up in the office with one of these things. This one's a nice challenge. There are a whole slew of them. They get more interesting. This is pretty nice. Turns out it's related to binary numbers. So if you learn about binary numbers, you can figure out how to do this one. This one, you're trying to get this long piece off. And anyway, so certainly throughout elementary school, nobody really plays with these puzzles in the sense of it's not a course and there's not a curriculum and here's how to do this puzzle and learn it for next week's exam. But it's kind of a neglected piece of mathematics in K-12, even higher mathematics. And it's a shame, because I think that we lose a lot of people who do have mathematical skills, but not just in the one that we're focusing on at the moment. And it's a nice opportunity to have a day like today where you get to see all sorts of mathematics that probably you've never seen before. How many of you saw something new today that you never thought of before? And it's kind of a fun experience to do that. I don't know if you share that fun with me, but I love to see new things. So along the ideas of topology, there's this old joke about what's the worst time of the day for a topologist? Breakfast, because topologists can't tell the difference between a donut and a coffee mug. Now the reason is, if you haven't got that joke yet, we'll let it sink in. But what topologists are allowed to do, you can change things and still call it the same. Like, if you had the handle of a coffee mug, you could pull it and stretch it, and it's still a coffee mug. You can even flatten the drinking part of it, if you like, so that when you pour the coffee, it just pours off. Right? Nobody's going to want to use that, but a topologist would say that's the same shape as a coffee mug. Right? It's just something with the shape of something with a hole in it. It's kind of like maybe like this rubber band. This is a donut, right? It's also a coffee mug. And I've made many a mess at home trying to prove that. So what I'd like to do is figure out, I'll show you a neat little trick here with coffee mugs. And be careful if you break these things, they'll smash over the floor, because they're ceramic, right? All right. So what I'm going to do is I'm going to link them together like this, right? And you can see that there's no way to get these apart, right? In topology, they call this a link, right? And even if you pull hard on it, there's no way, it doesn't matter how you do it. Now, one thing that you learn in topology is the reason it's impossible to pull these apart. Wait a minute, I must have done it wrong. Because they're apart. All right, let's try it again. We'll put them in and make sure that it's linked, right? You can't possibly do this to get them apart anyway. But what you can do is, maybe if you could come up here for a second, you could do a little magic with me. Can you come up? What's your name? Alex, come on over, Alex. I need your special abilities to blow on that, right there. Right? So he blew on it, and the blowing is what pulls them apart. So you might not have noticed when I blew on it, because I didn't puff my cheeks up. But thanks very much, Doc. So that's a topology trick. And those of you who are currently in topology, how many of you are taking topology now? Oh, we got one. All right. So that's your homework exercise. We're doing this every week, right? So I'll collect it next week. But you can actually think about, well, it certainly is impossible unless you do something. So what is it you must do? And you can email me and let me know. Okay, here's another one. It's a rope, a string. This is kind of a physics trick, along with topology. What we're going to do is just tie a knot in this, right? So we put it together. And what I'll need you to do, here, can you pull this through here? All right. In fact, why don't you come up with me? Okay, I'll pull it tight so we have a knot. All right. Ow, 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 not that. All right, so I'll take my finger out. Now, the thing about, everybody knows about friction, right? Friction makes things hard to sort of pull apart or that sort of thing. The opposite of that, it's on the commercials, right? Viscosity. So this happens to be a string with a very special viscosity, all right? Just like any other string. So what you can do is if you pull hard enough, it's not that easy because of the friction, but there is some, then you can actually pull the knot right off, right? You hold that up. There's no knot on there, all right? And I don't want to lead you around too much. All right, you can let go. So what's going to happen now is, here, why don't you stand over there? Doing a very good job standing, by the way. And what I'm going to do is I'm going to throw it to him, okay? Now, I have to be careful with this because what I want to try and do is get the knot back onto the string. All right? Now, because it's viscous, if I get it just right, right on the tip, it's going to slide right through. Okay? So let's see if we can do this. You ready? Now, you have to maybe, I don't know if I'm going to catch it, but yeah, let's see. Oh, man. Got it. All right. All right, I missed. I got to make sure they collide in midair. It's not a trivial matter. So here we go. Let's try it. I don't know if you can see it, but they collided. Yeah. Okay, so, all right, there's a lot of blathering on. This is, of course, a bunch of lying, right? My students definitely know that I lie a lot. And your object today is to figure out when am I lying, okay? I'm not a lawyer, so it's not when I move my lips, but sometimes. Okay, so those are some topology tricks. What I want to do is, topology is not my area of expertise per se. I like combinatorics, and if that word doesn't mean anything to you, then join the club. But what I want to do is describe a little bit of what combinatorics is and how it's used. And you probably all have a deck of cards at home like this, right? What I need is one volunteer, maybe, yeah, you know what? Let's do that. Why don't you come up? It's Sonia Robinson Day, right?
Julia.
I mean, yeah. Kowalski, yeah.
Different day.
That's right.
They're really the same person.
All right. Let's see. That's right. She's the actress. Right. Okay, so actually I don't need this, but what I want to do is show you a nice trick in honor of Mrs. Robinson. That was from the movie, right? I want to do something, you know, people, I hate this, but our society has sort of proliferated this for ages. And not only our society, but, you know, girls aren't good at math, blah, blah, blah. And I'd like to demonstrate why that is so blatantly false. With something that psychologists and psychiatrists have learned very recently, in the last couple of decades. Something that women can do mathematically that statistically guys can't do. All right? So it's kind of a fun trick this way. And what I want to do, for starters, is will you just pick 5 cards out, any 5. You can look at them or not look at them. You can hold them like this, and go ahead and just grab them and hold it. Yep. And then hand them, what is your name?
I'm Carrie.
Carrie, nice to meet you, Carrie. Let's give her a hand. 2, 1. Okay, you have 5 cards yet? All right, why don't you hand them to Carrie so I don't get cooties. And so what we're going to do, the interesting thing about this, and I'll describe this to you, Carrie. Yeah, you look at them. One of the things that that women have in terms of the way they arrange things normally is an ability to create order out of something. All right? And it's an interesting kind of phenomenon that's in some sense unavoidable. So I'll let you just kind of arrange them the way you want. And what I'll do is, let's see, how should we do this? We have a board here. Why don't you, when you arrange them in your favorite order, whatever that might be, go ahead and show me, let's see, the first 4 cards and then hide one. All right? And her pattern will be fairly obvious, you'll see. And maybe I might be able to see what the missing card is because of her order. All right? So as she's doing this, again, you just pick them how you like and put them in order from left to right. You'll put 4 up, and then you'll hide one. That make sense?
Just whatever I think looks
So whatever you think of, and we'll go around the room and we'll see if we can try to guess this.
Okay, so it's
Okay.
4 up and 1 down?
Yep. Anybody bring a drum? Do we have a drum roll? Pressure's on, Carrie. You have to do something arbitrary. And do it well. Okay, so she has, we can see, there's a 10 of hearts, then a jack of spades. No, diamonds. All right, I'm not really good at this, so I'll need your help. 5 of spades, queen of clubs, and then some card that we all have to guess. Anybody see the pattern? You want to try and guess what the fifth card might be? Yes? Something of hearts? Yeah, now everybody knows the suits, right? You go, I mean the cards, ace, 2, 3, 4, something, 8, 9, 10. Is that the something you meant? It's different. So maybe you think it's a heart. Let's see. I'll just venture a guess myself, unless anybody knows what it is.
I was thinking it might be not a face card. As opposed no face, not a face, face, not a face.
So it alternates non-face, face, non-face, face. That's a nice pattern, so it could be a non-face. So that's a good idea. Well, let's just see. How about if I take a turn, maybe I'll guess that it's the King of Hearts?
Yeah.
Well, I wanted to stay up here because we can do something even a little bit more fun. Is who wants to pick? Pick now. You want to pick some? All right. So then you'll give them to me. Any 5 you like. And we're going to make Carrie guess. Okay? All right. Now the reason that I'm good at this trick is I used to be a woman. And let's see. I'll just try. What would I do if, let's see, how about I'll do, you all see that? All right, and so what do you think it is? Eight of diamonds. All right, any other guesses? Would you like to take a guess? Seven of diamonds. Would you like to guess?
5 of spades.
5 of spades. Can we see? Well, how about you haven't had a chance yet? Why don't you guess?
You know, I think I really like his answer back there. So, 7 of diamonds. That sounds pretty good.
7 of diamonds?
Yeah.
Not bad, not bad. Thank you very much. I've been performing this trick for quite a long time, and this is the very first time I've had an audience member guess it. Very good. So apparently some men can do it. I don't need this yet. I'm going to need this space back here, okay? I'm going to run over your toes for just a moment. If you don't mind that hurting, but I think we're going to need to try. So let's see. Here's, I'll do what magicians are not allowed to do. I'll tell you how it works. Okay, as you can clearly see, this is an old trick, by the way, invented by somebody named Fitch Cheney. Fitch Cheney apparently was the first, he received the first mathematics PhD ever at MIT. And then he went on to teach, I think it was at the University of Connecticut, and after that, University of Hartford, where I grew up. Just so happened that sometime later, the chair of the University of Hartford was Joe Kagan. Joe Kagan used to get his papers delivered to him in the morning by someone who looks a lot like me, but used to be a lot younger. And so there are nice coincidences in the world. I can say that. So let's see how it works. I call this the fifth card just to talk about it. And let's see if we can focus that. So let's see how it works. All right, so how many suits are there in a deck? 4, right? Clubs, diamonds, hearts, and spades. So 4 of them. Now, if I give you 5 cards, what can you tell me about those cards and suits? There's got to be an overlap, right? There's got to be some 2 cards that share the same suit. They can't all be different suits, right? Historically, we call that, the pigeonhole principle. And you know how in movies, they often have at the very end some line that says, no animals were harmed in the filming of this movie? Well, science isn't always quite that way, because they discovered this by stuffing pigeons into holes. And it's very gruesome. Okay? So what happened is they learned that if they had 5 pigeons and only 4 holes, there's going to be some damage. And so that's the idea. Okay, this is the part where okay, so we're going to take advantage of that. What we're going to do is first find somebody that you know very well in the audience. Especially if their name is Carrie and you've rehearsed this trick. That's the first thing. Is we go way back. All right? I don't go as far back as she can, but so we practice this trick together, and that's the first rule of magic is, definitely cheat. So, so what we agreed to do is to have on the very left and the very right the 2 cards that matched in suit. Now you may have more that match in suit, but just some 2. Okay? And so when she showed, what was the first one? It was 10 of hearts?
Yep.
I knew that the card that was hidden was going to be a heart. Okay? Now it's a matter of which heart. Well, there are 12 other cards in that suit, right? So I just guessed. After I figured out some stuff. So what did I do? I knew that there were 6 cards after the 10 and 6 cards before the 10. And we arranged it so that the card that was hidden was going to be one of the 6 cards after the 10. That is if you wrap around. So what are they? Jack, Queen, King, Ace, 2, and 3. Right? So I knew it was going to be one of those because we arranged it. But what if it wasn't? What if she picked the 6 of hearts? Then we couldn't do this trick, right? Yeah, she would have shown me the 6, and then the 10 would have been one of the 6 cards that came after it. Follow? So she's got the choice. It's sort of which ones are closer to the other. And so now we've narrowed it down to just one of 6 cards. All right? Well, now your odds are better if you want to guess, but you still have some material that she can work with. There's this information about the 3, what I call scorecards in the middle. And she's going to arrange it so that that encodes a number from 1 to 6. Now, let's say you had 3 people that have to line up, right? Yogi Berra did this once when he was managing the Yankees. He told his team to line up alphabetically by height. It's my favorite Yogi Berra. But if you were going to just line people up in any way that you like, how many ways could you do it? Well, the short person could be first, second, or third, right? And then in the other 2 positions, they could come either in order of height or out of order of height, right? So that's 3 times 2 ways to arrange these 6 cards. Or if you like letters, if there are ABC, you could write ABC, ACB, BAC, BCA, CAB, and CBA, right? Those are the 6 arrangements. Well, in fact, that's what we did. We arranged those to be the numbers from 1 to 6. If they came alphabetically like that, we could arrange for each one of those to encode a number. So we sort of memorized that code, or thought of it like looking at letters in a dictionary. You know which comes first. So you have that the show and the high cards have the same suit, and then whatever you calculate the score to be, you add it to the show card. So if I'm not mistaken, she scored a 3. And so from the 10, I counted up Jack, Queen, King. And that's how I knew that it was the King of Hearts. Okay? And so that's a nice example of some combinatorics. Combinatorics, the root word is combinations. So how many combinations of doing this or that are there is a key question that we have in lots of contexts and things that we care about. And most people like me, we don't really care what it's applied to. We just like to have fun with it. But luckily, I wouldn't have a job unless there were applications for this stuff. And you find them all over the place. When people are working on decoding the human genome, or when people are sending secret signals, across the internet, or if you bouncing, messages off satellites or things like that. All these things involve combinations and codes and things like that. And that's kind of what I'm going to do today, to show you lots of tricks that have codes in them. They're really kind of fun. All right? And so, let's see if we can think about, and as you get older, there are all sorts of questions that come up in terms of, well, I'll even skip that stuff. So let me go right to the tricks, because that's a whole lot more fun. All right. So maybe move this again. Let's see, what should I do next? How about, I'll need another person from the audience. Anybody want to do it? And my daughter does. We'll do it at home, then. And why don't you come down? And I'll need a deck for this. Hi, your name is? Not so. I have never heard that name before. I thought you were going to say it until last week. No, the last time was it. When was I? All right. Never, ever, but tell your mom I said hi. All right. Okay, so what we're going to do. I don't know. No, I'm not trying to say halfway.
Oh,
Past
a third or
could be 3/4, could be. It's got to be. This usually isn't the hard part of the trick. One never knows. Okay, now I'm going to double your chances again. All right? You like those odds? And we're playing for all the books at this table, is that right? Okay, so I'm going to double your chances because when I say cut to your card, it could be in two places. It could be the bottom of the deck on the top, or it could be the top of the bottom part. You see what I'm saying? Cut to your card. There's two cards there. So now he's got a one chance in. There was 1 out of 26, but now it's 1 out of 13. Thank you. You must have a father who's a professor at ATU. So, okay, so let's check. All right? We'll first check the bottom card of this top deck. All right? Any rolls? Nice. Nice. Okay. Is that your card?
No.
All right, so it must be this one. Is that your card?
No.
No. Wait a minute, but you promised me. You said that you were going to cut right to your card. You heard it.
I did.
First, it was cut exactly half, and it was. Let's try it again. Let's try it again. Okay, now, one of the things about this trick, actually, you know what I forgot to do? I forgot to turn those two cards over. They're still upright, so maybe I should fix that. Do you see two cards here that are face up?
Yeah.
Well, in fact, you can see a card in between them. Would you get rid of that one for me? And would you show that to the audience? You know, I once interviewed at NSA. Anybody ever heard of NSA? They've been getting a bad rap these days, so it's really good. It is a great place. The National Security Agency employs the most number of mathematicians in the whole planet. It's like a little city there in between, Baltimore and Washington, D.C. It's fantastic. And I think we have someone who might be working there next year in our front row. But if I told you who it was, I'd have to kill him, or I forget how it goes. But when I interviewed there about 20-ish years ago, let's say 10, so I'm younger, and there was a guy named Brent Morris there, who was the director of the Math Research Group. And Brent noticed on my my Vita, it said that I had this, passing hobby or interest in mathematical card tricks. And so his first question was, "Did you bring any cards?" I said, "No, I mean, I just was coming for this interview. I didn't plan, He's like, "Well, let's see if there's any around here." "Oh, I might happen to have one." So that I'm in trouble now. And sure enough, he showed me that trick, and we traded tricks for about an hour. And then somebody came and said, "Okay, now we've got to take him to here." And Brett said, "I haven't even interviewed him yet." So I didn't get the job. All right. So maybe let's do another one that's kind of fun. How about here's a neat one. I'll get this up here again. Let's see. We need another person. Somebody who. How about you? Can you come up? This is a good numerical one. I think you like this. All right, what's your name?
Tori.
Tori?
Yep.
With a T?
Yep.
Nice to meet you, Tori. What grade are you in?
Sixth grade.
Nice. 6th grade. What school? Santan. And what's your teacher's name?
Monica Kennedy.
Monica Kennedy. She's nice? All right. Here's what we'll do on this trick. Make sure I've got all the cards that you okay, quick count. Why don't you pick any card that you like? All right. And just put it on the table there. Now I'm gonna ask you to think of a number between, say, 1 and 50. All right. And you got one?
Mm-hmm.
Okay. Don't say it. But take one of those markers and just write it on the board. That way I can see it in the back of my head. All right, tell me when you're done.
Done.
Done. Okay, so what you want to do is divide that number by, let's say, 8. Now, you have to remember that when you divide numbers, you get 2 numbers out of it. You get what most people know as a quotient, and one that's a remainder. So that I don't have to look. Do you remember what the quotient part is? You divide your number by 8, and you get something plus a little extra, right? What's that something?
Remainder?
Okay, so not the remainder, but just the number. Go ahead and divide this in your head by 8. And you might get a number like 3 and some extra. Or what do you get? How many 8s are in here? You know the answer? We'll give you tenure if you get it. Anybody want to help him out? 4? You agree 4? So that means that, okay, so 4, that's good. And then, now there might be some remainder. It could be it divides evenly, exactly. Or it could be that there's some extra 4 8s plus some extra. So what do you get when you do the remainder? So he says a remainder of 3. Everybody agree?
No.
No, they got something else. So let's see, 4 times 8 is 32. plus what else do you need to add to get to your number? 7. Right? So now I know what his number is, right?
Of course.
39. There's more. So you said the quotient was 4. So let's take those 4 cards and we'll just move to the top. Does that sound good to you? Sound great. All right. So now I'm going to just shuffle the cards 3 times. Okay? And let's see what happens when I do. So you've got, said your remainder was 7. So here's the first. This is the part where I need my glasses. So here's a shuffle. Okay, that's 1. And then another shuffle. I've ruined a lot of cards doing this because one of these days I'll have to learn how to do it the fast way. Any fast shufflers here? That's the Indian way. You know the one where you take each half and you kind of...
Not a gambler, so
Somebody call it riffle shuffling or something like that.
not too easy.
The department chair came to aid me. I don't need your help with this trick. I just need travel money. Okay, so you have to be careful because you can smash his notes.
There's a no trouble.
No trouble. I'll take you for the next one now.
Leave that bucket.
Okay, he said his card. His number is 39, right? All right, you have to help count this for me. So that's
2, 4, 5, 6, 7, 8, 9, 10, 11, 14, 16, 18, 20,
okay. So we learned 2 things. I can divide. Sum up. Okay, so let's do one more and then I'll try to explain a few things. All right? Let's get a bunch of people up here. How about, can we get 5 of you this time? You in the back. Yeah. Come on up. Even if it was an accidental, somebody else put your hand up. And can you come up also? And how about you right there? That's good. And can you come up? Good. And you haven't come, right? Give you a chance. Come on up. Yeah. How are you guys? Do you have fun today? All right. All right, so if you guys could just all line up in a row right here. Do a fun trick wherever you like. Maybe just right in the middle. Straight line. Good. Okay. Now start marching. No, it's okay. I just wanted to say that. I always want. All right, so here is kind of a fun thing. Maybe I do need this again. What I want to do this time is, this is kind of a statistical trick. So for starters, let me get rid of all the jokers in the deck. And two jokers and some other kind of card special offer. I need somebody who is a good shuffler for this one. If If only my chair was here. Ah! You play a lot of poker? Bridge? Poker, that?
Vegas.
You used to. Are you free on Monday nights? Okay, so what I need you to do is shuffle these together sort of like that. Oh, that's good. Yep. All right. So here, this is a trick that I use with a little more than half the deck instead of a whole deck. My wife is always telling me I'm not playing with a full deck, so let's prove her right. So anybody know how many shuffles you need in a full deck to really kind of randomize the deck? About 7. It's really about 6.5. Percy Diaconis and some graduate students, I think, were the ones who proved that. Anybody know what a half shuffle is? Half shuffle?
It's when you drop the cards.
You just shuffle half of the deck. And they're pretty random. All right, so I don't want to do that. All right, so what I do want to do is I want to get rid of about half the kids. So let's get rid of the high cards. I'll do this trick with just the low cards. Ace will be low. So everything from 9 and above, let's get rid of. Okay? You want to check that? You do this? So, so we'll get rid of that's Jack, Queen. Okay, so we'll just get rid of the high cards. Now, that's high, right? 9 and above. Am I missing any? So my sister. Anybody play Crazy Eights? Who plays Crazy Eights? It's like the old school Uno, right? She used to. My sister. We played this a lot, and she used to cheat a lot and always get me on the 8 and 9. She was hiding somewhere. So I'm not going to do the 8 and 9s either. Just in honor of Julie Robinson. Aces are low, right? Okay, so get rid of some more of the high ones. And I think we got them. So how many cards did I get rid of? Let's just make sure. Let's see, 9, 10, Jack, Queen, King. That's 5 cards, but 4 suits, somebody said earlier, right? So that's 20, plus the 8 diamonds makes 21, right? So are there 21 cards there? Just let's make sure. And we'll know. Okay, so now, you can take those home too. And so this trick is one that's more statistical because now that they've been shuffled, they're kind of randomized. You got 21? Okay. So we said 6.5, and with just 5, with just 31 cards left, I guess. Let's just do it 5 more times. We'll shuffle. So I'll shuffle, and each of these people can cut once, right? And then we'll have it really randomized. And that way, statistics will kind of come out nice. So here's the first shuffle. And now I want you to cut the cards. So anywhere you want, you can lay your hand. All right, so that's 1. And 2. Okay. All right, you getting ready for this? How old are you? 6. My daughter is in the back. She's 6. And how old she's going to be next year? Did you know her? How did you know that? Oh, yeah. All right, you're getting cut now. When are you going to turn 7? You're good at that. Do you play poker? No, really, what do you do on Monday nights? Are they good for you? in. All right. There you go. So how many have I done? Anybody keeping track? 4. Okay, so let's do one more. And that's 4 income. Okay, last one, and then you get to cut. All right. So now they should be just completely randomized, right? Why don't you get one more cut, young man, whatever your name might be. Okay, final cut. Okay, and so now we'll just give the top card to each person. Here, why don't I start with you? And then you. Okay, everybody gets one card. Now don't show it to me, but you can look at it. All right? Now everybody knows there's 2 kinds of cards, right? In fact, I don't know if you know this, there are 3 kind of people in the world. Right? Those who can count and those who can't. I'm not sure you like that one. But there's 2 kind of cards, right? There's red ones and black ones. Okay? So now in this statistical experiment, we have a deck that has almost the same number of reds as blacks, right? And you have 5 people here, each with a card. Okay? So you should expect about how many red cards and how many black cards?
3 black and 2 red.
3 red and 2 black, or 3 black and 2 red, right? In fact, it's not quite equal that we started here, right? There were more reds than blacks, or the other way? They took an extra red out, so there are more blacks in here. So what do you think will happen? Were there more blacks or more reds in this group? Maybe it's more likely to be 3 blacks. Okay, so here's what we'll do. Look at your cards, and just raise your hand if you have a black card. All right? And how many did we get? 3. Pretty good, huh? Okay, that's not the trick. Here's where the interesting thing comes is what we'll try to do is, we'll just look at, well, your card is black, right? So how many black suits are there? And they're called spades and clubs, right? And if you just had to make a random guess, what do you think it might be? Do you think it's the spades? Would you think it's a high spade or a low spade or low spade? Well, let's see if it's a low spade. Is it the ace of spades? Not bad. Ace of spades. Good guess. Who guessed that? And the next one's black also. Now, what do you think? Well, we've already seen a spade, so it's probably a club and, well, high, low. Anybody guess a 7? No, don't guess a 7 because it's a 3, right? Is it 3 clubs? There you go. Very nice. He's good. I think he's done this trick before. That was a good job. Okay, and then finally we have a red card, right? So maybe, who knows, a diamond, heart. Show of hands, anybody think it's a diamond? And who else thinks it's a heart? This is how I know how many Americans in the room, because only about 40% of you voted. And some people who voted twice for Chicago, I think. Isn't that the motto? It's vote early, vote often. Yep, there you go. Okay, so let's see. You have a red card, and everybody seems to think it's a, well, you voters think it's a 7 of diamonds. 7 of diamonds. How about that? Very good. Very good. All right, where are your parents? And then it must be the 7 of hearts and the 7 of spades. How about that? Very good. Thank you very much. All right, how are we doing on time? So that means?
About 2 more.
Okay, 2 more hours. All right, so maybe it's a good idea to try and describe a little bit about some of these tricks. Diaconis is a famous mathematician at Stanford. He was for a long time at, what is this term here? At Harvard before that. But before his mathematics career, he was a professional magician, was known as one of the best second card dealers in the world. Anybody know what that is? When you're dealing something other than the top card. And he used to do a lot of things to debunk. In the 70s, there's this big fashion that you could proclaim you had special powers and stuff like that. And he would debunk this, and he was kind of angry. Why don't you just call yourself a magician and leave it that? And so he had fun doing that. But he was credited with some of the best tricks of the century, and that last one was his. I added some extra parts to it because I teach a course in cryptography every so often, and that trick is a nice example of cryptography. Now, the first trick that we did with Carrie was more in line with coding theory. Now, coding theory is when you're just trying to send message to somebody else, and you don't care if somebody else figures it out. You just want to safely do it. And that's the kind of thing that when you send a signal off a satellite to get good, a TV picture or something like that, you don't care if anybody intercepts it. You just want it to make sure that the picture comes out nicely. And what happens is it bounces through space and electromagnetic radiation and all sorts of things like this change bits of zeros and ones. And what you'd like to do is when it's received, it's certainly going to be different than what was said. And you'd like to make sure that you can detect whether or not there was an error, how many there are, where they are, and be able to correct it. And it's called error correcting code. It's fascinating. And some of it involves the mathematics that I did to be able to do those tricks. Cryptography is a little bit different. That's when you're trying to do it secretly. So you don't want anybody who intercepts your signal to be able to figure out what you're saying. Okay? Great wartime history to this, but I'm not going to go there. But what's even more important is not letting somebody know that a signal was sent. So, for example, if you can randomize your signal first, then to somebody receiving it or trying to intercept it, it just kind of looks like white noise, and they won't be able to even know that a signal was sent. If you can do that, that's great. And that's a little bit like what the shuffling was in the beginning of this trick. It's an example of how you mask randomness. You make something look random that, well, really wasn't, right? Somehow or other it wasn't random. I'd like you to think that it was, because it looked better, but it wasn't. And so that's one of the neat things. And then, of course, being able to encode it with some sort of secret thing. So I can't tell you too much of that trick, but I'll tell you about the others, and maybe you can guess at some ways that the final trick was done. Here's that first trick that we did with the number. I think it was 39, right? So we divided by 8. And so we rounded up. Then let's see, we cut those cards, and we shuffled it 3 times, and then we found exactly what card we wanted to. So that's how it kind of looked. And then let me show you a little bit about shuffling. I'll try to do this quickly to not take too much time, but everybody can read time. And one of the things that you practice in elementary school that's critical is this quotient. How many buses do you need if you have, 105 kids and 25 kids can fit in a bus? Well, you divide and the quotient tells you how many buses, but of course you need maybe one more than that. But in a lot of mathematics, it's the remainder that's the most important part. So for example, if it was 10 in the morning and somebody asked you, what time is it 5 hours later? What would you all say? 3, right? If you're in Europe, they'd actually say 15. But we kind of make it simple because we're not good with higher numbers. So we reduce it. So really all you care about is the remainder. If you get rid of all the 12s, you're left with 3. And you can think of this as clock arithmetic, but The modulus here is this fancy word we use for how many numbers are on the clock. But you can do it with 7-hour clocks, things like that. And so sometimes you can divide, but sometimes you can't. Like if you tried to divide 14 by 2 on a clock, normally you'd think 7. Right? But it could also be 1, because 14 is the same as 2 on the clock, on a 12-hour clock. Right? If you look, it goes around, and half of 2 is 1. So you could get multiple answers. Or sometimes you can get no answers. Right? So if you wanted to divide 3 by 2, you don't get a whole number. Because 3, 12 more than that is 15. That's the same as 3 mod 12. They're all odd numbers. You can't divide it exactly by 2. So you have to be careful. And so sometimes when you try and do things like algebra in these modular systems, you have to be careful when it works and when it doesn't. Now, with shuffling cards, you have these things called perfect shuffles, which are very interesting because what you can try to do is split the cards exactly in half. So it's a little bit hard to show you with my finger, so let me shrink my finger a little bit. And you might have 7 cards in a deck as an example. And you can cut it in half sort of by a pack of 3 to a pack of 4 or vice versa. Right? And what somebody could do if they practice for 30 or 40 years is, of course I'm still in my 20s, so that's not me, is try to take them one at a time and alternate them. So shuffle it so that you alternate the cards. All right? And what that's useful for is making somebody believe you've actually randomly shuffled in a sense. But there's a nice pattern when you do that. You look at the cards that started in positions 1, 2, and 3, and they ended up in the new positions of 2, 4, and 6. So they doubled where they ended up. And the blue ones, 4, 5, 6, 7, 8, they also doubled. If you double them, you get 8, 10, 12, and 14. But if your clock only has 7 numbers on it, then a number like 8 is the same as 1 mod 7. It's 1 after 8. And 10 is 3 after 8, and so on. And you notice that all those numbers are distinct. They're different places in the deck. And sure enough, that's where the blue ones ended up, in the 1st, 3rd, 5th, and 7th positions. So if you can do what we call perfect shuffles, then you can kind of keep track of the cards a little bit. Okay? And so you just have to then get used to doing a lot of arithmetic in your head. Now, if you have an even number of, and it's interesting that this was called Faro shuffling back in the 1800s. There was a Wild West game called Faro that was a popular game out in these here parts. And if a dealer could kind of keep track of the positions of certain cards, he could really make a killing on innocent bystanders who came and laid their money down. So don't use my travel money on Faro. Okay, so, but this kind of shuffling became popular from this game Faro, so they used to call it Faro shuffling. Of course, in our nice American ways, I'll tell you how they spelled it. Everybody knows how to spell Faro, right? It's a very unique spelling, F-A-R-O. So our educational system maybe has actually gone uphill since then. I think we have better spellers. If you have an even number of cards, it's a little bit trickier. So some of the tricks I actually tossed a card. Some of them I kept even for different reasons, but some of this algebra of multiplying and adding and so on, yeah, you can keep track of if you figure out. But there are 2 types of shuffles. There's in shuffles. If I had, say, 3 cards here and 4, let's say I had 4 and 4. This was the top part. I pulled them apart. I could do an in shuffle where you see how the top card went underneath, or it could go above, and that's called an out shuffle. And so there are two types of in shuffles and out shuffles. And for keeping track of this number 39, when I asked for the remainder, after you divide by 8, was 7. And for reasons I won't describe, I subtract 1. What I do is I think of what's the binary representation of that. Now, binary is you think of how many powers of 2 add up to this guy. So it turns out to be 4 plus 2 plus 0. And so there's 1 4, and 1 2, and no 1s. And that's case 2. And so this actually makes me do an in shuffle, an in shuffle, and an out shuffle. And 110, like I-I-O, is a nice way to remember it. And so I can send the card to any place in the deck I want by keeping track of binary arithmetic, modular arithmetic, adding stuff together. So a lot of times, learning some extra kind of crazy things besides just the normal arithmetic you learn is very useful. And of course, this is just fun for magic, but this is used all over the world for lots of very sophisticated applications. So I think maybe this might be, given the time, the best place to stop. What I'd like to also mention on a day like today, quite often I'll sit on an airplane as I'm traveling somewhere and somebody say, what do? You get into that kind of conversation. And, I say, I'm a math teacher, right? And you see them start to reach for that little bag in the front. You kind of hope that it doesn't get messy. But after a while, I started changing my answer. And I would say, I'm a coach at Arizona State University. They get all excited, right? Oh, wow, I'm sitting next to like the basketball coach or something. What do you coach? And then you say, mathematics. And they just, it's like falling off the cliff. It's a great, it's fun to do. So, but it's a shame that you get that reaction. In a lot of other countries, I had a friend spend some time in Budapest for a semester. And he met somebody, this woman he was chatting with in a coffee bar. And she said, what do you do? And he got ready for the classic answer and said, math. And she said, oh, I love math. And he thought, okay, well, let's see, the next one is usually until 4th grade or something. And she said, and so he said, really? What's your favorite proof of the Pythagorean theorem? And she had one. It's a true story. It's a great country. So, but what I'd like people to know out of this, now that it's not the only reason to go into some career is how much money you're going to make. You should really go into it because you love it. And you find out a lot of us who teach at this level love it. And you have to, because Wayne really works as hard, and in order to put up with that, you really got to love what you're doing. But it's also good to know that really and truly you can make quite a living if you, this is every year since, I think, the Neanderthals, they run these studies that say, what are the best professions? And they rank them on what your salary is, what your benefits are, what your level of stress, all these types of things, and what your projected advancement opportunities are, things like this. And every single year since they've been doing this, math is in the top 3. A mathematician often has the top 3 jobs because they go under different names of like computer science or actuary, things like this. Every year, it doesn't matter if it's a great year, we're up there because the finance people are doing well. It's a bad economic time these times, but it's now people need mathematicians more than ever to do financial analysis, projections, planning, all sorts of things like that. And it doesn't matter, it seems to be that we're always up there. And this is from asking people 10 years after their degree. So they've had time to advance. A lot of these people are in management because they figure out how to solve problems. And those problems might involve people. So they go into management and they get advanced very quickly. And so this is a nice indicator. I'm really excited to have so many of you here today. And I hope you can pass on that word that there's really good reason to study math. not just because it's fun and you can do magic. So thank you.